And now we go to so another more general study of critical points. So the study of critical points. And first of all, what are critical points? A critical points x bar of a function f is a point of differentiability of f, a point where f is differentiable. Moreover, where f prime of x bar is equal to 0. It is also called a stationary point. Okay, so we immediately give the theorem, which tells us what are these stationary points, whether they are minimum points or maximum points, and so on and so on. We can have this information only by studying the derivatives. Perhaps the first and second derivative can be sufficient, but sometimes you have to go farther and farther. So the theorem is the following. You consider a function f of class Cm in AB, an interval AB. X bar is a point in AB, and f prime of x bar is equal to 0. Now, first, suppose that all derivatives fj from the first up to the derivative of order k minus 1 are equal to 0, and fk of x bar is different from 0. And suppose that k is even. Sorry, not f. K is even. Then there are two possibilities. 1a, you have fk of x bar larger than 0, then x bar is a local minimum point. And here I have to add a word that is very important, which is strict. And let me here write what is strict. Strict minimum point. Strict means that there exists a neighborhood of x bar such that for every x in this neighborhood u, we have that f of x is strictly larger than f of x bar. This is why one says strict. Strictly larger. This is a stronger information than the definition of minimum, because minimum just says that it is larger or equal. F of x is larger or equal than f of x bar. Okay. This is the... And now, in this case, we have that this is strictly large. So this is 1a. Second, 1b. Fk, remember that k must be even, we are in the case of k even. Fk of x bar is smaller than 0, then x bar is local, again strict maximum point. Okay, this is the first case. The first case corresponds to k even. In the second case, we have almost the same hypothesis. Where we have fj of x bar is equal to 0 for j equal to 1 up to k minus 1, and fk of x bar different from 0, but this time k is odd. Then x bar is not a maximum nor a minimum point. It is a horizontal inflection point. Okay. Now, let us give some examples in order to understand the information here. First example is the study of function that we developed earlier. So f of x is equal to x e to the minus x. Okay? We saw that f prime of 1 is equal to the value of the prime derivative 1 minus x e to the minus x evaluated at x equal to 1, and this is equal to 0. So 1 x bar equal to 1 is the only critical point to be discussed. Now, the first derivative is equal to 0. In order to understand what is the nature of this point, either we study the sign of the derivative, as we did before, or you follow the last theorem and you just evaluate the sign of the subsequent derivatives. So, let us go to the second derivative. So the second derivative is, f second of x is minus e to the minus x, and then minus 1 minus x e to the minus x. So it is x minus 2. Equal to x minus 2. E to the minus x. So f second of 1 is equal to minus 1 over a which is smaller than 0. So this is the case 1. B. So the first derivative, which is different from 0, case derivative, is even, and this derivative is negative, so x bar is a local strict maximum point. Then we fall in the case 1b. Therefore, x bar is equal to 1 is a strict local minimum point for the function f. Sorry, not minimum, maximum. Maximum point. This was already easily deduced from the graph just using the first derivative here. Okay? Then another example, second example, f of x is equal to x cubed, for instance. So f prime of x is equal to 3x squared. So f prime of 0 is equal to 0. F second of x is equal to 6 times x. F second of 0 is equal to 0. And f third of x is equal to 6. So f third of 0 is equal to 0. So the first, is equal to 6. So it's different from 0. So the first derivative different from 0 obviously calculated at point 0 is the third one. So we fall in case 2. In case 2, and x bar equal to 0 is a horizontal inflection point. So the horizontal inflection point is this one. Here we have graph. So the tangent is, so f prime of 0 is equal to 0. So the tangent at 0 is horizontal. And moreover, you see that the function is increasing, so one says that it is an ascendant horizontal inflection point. So because the shape is this, it is going up. Sorry. Here we go to the third case. We have f of x is equal to x cubed f of x is equal to x to the m, with m natural and m larger or equal to 2. So we have that the first, following exactly the same method as in the previous example, so we have that the first derivative, which is non-vanishing, the first non-vanishing derivative as the mth, because we have that fm of 0 is equal to the factorial of m, which is larger than 0. So if m is even, we have that 0 is a strict local minimum point. If m is odd, then 0 is a horizontal ascendant inflection point. And these are the different pictures between the two cases. So in the case of m even, we have something that can very qualitatively remember a parabola. But here at 0, it is much flatter than a parabola. So this is x to the m for m even. On the other hand, here you go to x to the m for m odd. And here, of course, we have we are in the case 1a. So we have a local strict minimum point. And here we are in case 2. We have a horizontal ascendant inflection point. Okay, and this is the prototype you must have in mind in order to prove the theorem. And now we go to the proof of the theorem. You will see that with this forward, it is extremely simple. The theorem of the relationship within derivatives and critical point. So case 1, k even. So we can use Taylor expansion up to the kth degree. So here we have fx minus f of x bar is equal to f prime of x bar, x minus x bar, plus f second of x bar, x minus x bar squared divided by 2 plus up to f kth derivative of x bar divided by the factorial of k, x minus x bar to the kth power plus Lie law of x minus x bar to the k, and Lie law is to be understood as kx goes to x bar. Now, by hypothesis, all these derivatives f prime of x bar, f second, and so on, are equal to 0. So we end up with this. This is equal to fk of x bar divided by k factorial times x minus x bar to the power k plus little o of x minus x bar to the kth power x going to x bar. Okay, now f of x minus f of x bar divided by x minus x bar to the power k is equal to, we just divide by x minus x bar to the power k. Of course, x is different from x bar in order to perform this division. And this is fk computed at x bar divided by k factorial plus little o of 1 for x going to x bar. This means that the limit for x going to x bar of this first member of this equality of f of x minus f of x bar divided by x minus x bar is equal to fk of x bar divided by k factorial. And so by the permanence of sign, sorry, this is x minus x bar to the k. By the permanence of sign, okay, the sign of this expression here must be locally equal to the sign of this. This as a sign, this is not 0 by hypothesis. The case derivative, the first derivative, which is not 0. So by the permanence of sign, there must exist a neighborhood U such that for every x in U minus x bar, we have that the sign of f of x minus f of x bar divided by x minus x bar to the k is equal to the sign of f of x, fk of x bar divided by k factorial, which is equal to the sign of fk of x bar. Okay? Now remember that since k is even, we have that x minus x bar to the power k has a positive sign. Then it is the sign of f of x minus f of x bar, which is equal to the sign of fk of x bar. And now there are the two cases. Therefore, if fk of x bar is negative, then f of x minus f of x bar is negative for every x in U minus x bar. That implies that f of x is strictly less than f of x bar for every x in U minus x bar. And this means that x bar is a local, strict maximum point. Okay. Vice versa, if f case derivative at x bar is not negative, it is positive, then f of x is larger than f of x bar for every x in u minus x bar. Therefore, so there exists u such that x bar is a local, strict, again, minimum point. Okay, this is the first case, k even, and now we go to the second case. So here k even was important here to say that the denominator here is always positive. And case 2 is k odd. So computation is the same, up to here. So let me copy, paste. But this time, since k is odd, we have that the sign of x minus x bar to the power k is equal to plus 1 if x is larger than x bar, and minus 1 if x is smaller than x bar. Therefore, we have that the sign of f of x minus f of x bar is equal to the sign of fk of x bar times the sign of x minus x bar. And this sign here changes in a neighborhood. Therefore, sign, of f of x minus f of x bar is not constant in any neighborhood of x bar. It changes when crossing x bar. So x bar is not the maximum nor a minimum point. It is called a horizontal inflection point, but in order to understand it, up to now it is just a name. In order to understand why this name is appropriate, you have to introduce the notion of a general inflection point and the notion of convexity. And we go to convexity by using this theorem in the next video.